Okay, right. So we are pleased to have the third lecture about black holes and operator algebra by Professor Erik Verlinde from Amsterdam and Simon visiting professor at Trinity College. Please, the station.
All right. Yeah, let me need to remind you a little bit of the things I talked about. Today I will discuss a slightly different topic, but I want to put it in context. So the algebras that I defined were type 1, type 2, and type 3, where the main distinction has to do with the properties of projectors. So in this case, there would be minimal projectors, which basically means that, well, there you can define individual states, which is not possible in type 2 or type 3 algebras. Type 2 algebras have also a property called finite projectors, which means that you can project on subspaces where you at least can order your projection and you can measure by how much the space is smaller. So this is called finite projections. And actually in the type 3 case, neither of these things exist. So the projectors are neither minimal nor finite. The fact that finite projections are possible allows you to do, well, classify what kind of projections are possible. And then this is what I discussed last time, where we talked about the Jones construction. Actually, there's something called the Jones index, which was classified by Jones and actually defines for you the ratio between the dimension of one projection and the other one. So if you project onto a subspace, you can at least count what is the relative factor that is in this Hilbert space. So this led to these diagrams which I showed you, which eventually became these knot polynomials. The reason why I'm interested in the whole development of, well, including von Neumann algebras in the discussion of gravity is that if you think about quantum field theory in space-time, it's actually described as a type 3 algebra. And indeed has many properties like locality and Lorentz invariance that kind of we think about now as sort of being emergent. And the idea would be that you indeed think about a underlying theory that would be described in sort of more like in ordinary quantum mechanics. So what I'm describing here, by the way, are factors in the sense that you talk about algebra describing only a subset of your system. So naively, you can think about it in the following way, that you indeed have a quantum system where we can only access part of it, and our algebra A, which is the Neumann algebra, only acts on one side. And so then there is also a set of commuting algebra operators that we call A prime. And this already sort of splits the space into two parts. And part of what is distinguishing these algebras is the amount of entanglement, or the way that the entanglement is described between these two sides. Now, this picture should also remind you of what horizons look like, say, near black holes or something like that. And this is actually indeed the application that I will have in mind. Now, the new thing that I want to explain now is that there's actually connections between these algebras. And the reason insight that sort of came about is that indeed these two algebras can be related. Actually, it's known in the mathematics literature, but it's given a new interpretation that when you add gravity to the quantum field theory, somehow the algebra of operators which you associate with a part of the space-time is no longer a type 3 algebra, but actually becomes a type 2 algebra. And that allows you indeed, well, to do more things like having finite projections and so on. And what I will say in the last lecture, and hopefully I get to that, is that these ideas of Jones actually then become possible in order to indeed understand more about, well, how information can be sort of transferred even from, well, things behind the horizon to the other side of the horizon. Now, in this lecture, I want to explain indeed the constructions that were recently sort of, how to say, introduced in this context, but of course already known by mathematicians, about relationships between these algebras, and it goes under the name of called the cross product. So before getting to the theory of type 3 algebras, I want to explain what is a cross product just more abstractly, just from the mathematics point of view.
Was it von Neumann who introduced it also now?
Yeah, I think von Neumann already knew about that. And the applications that eventually well, went to even classifying these type 3 algebras are due to Sakazaki and Pond in particular. That much later. So von Neumann had not much to say about type 3 algebras because, well, they knew they existed, but he thought they were really complicated. So the idea of a cross product is abstract just when you have a group action. But it turns out that in these type 3 algebras, they're a very natural group action that you can talk about. And then when you apply the cross product construction, you actually can connect to type 2 algebras. And that actually allows you indeed, as I said, to use many techniques that we know from type 2 algebra that are possible to say things about the type 3 situation. But
By the way, I once was probably in a third lecture. These algebras have groups.
There are groups, but actually the groups I will talk about are not very exciting. They actually abelian groups.
No, I meant the type 1 algebra, let's say. Is there a type 1 group for which this is an algebra?
Well, associated to any group, you can write a type 1 algebra. I will mention some of them. If you take the algebra of bounded operators on the square integral functions on the group, that would be type 1 algebra. But if it's, of course, it depends if it's an infinite dimensional group, yes or no, it becomes more tricky. The thing that, well, I will indeed, well, explain a little bit today, but more of it next week, is that this idea of cross product can actually, in the gravitational context, be thought about as some kind of gravitational pressing. And but so let me first explain you what it is, because intuitively I think everyone kind of well has a feeling for it, because it's somewhat like what you know in group theory itself. If you have a group and there's some other outer automorphism acting on the group by, well, there's another group acting on it, I can take a semi-direct product. So I'm going to assume now that I have an algebra. And with a group action, let's call it G, and I will need to think about it as an outer action in the sense that the group generators are not part of the algebra. They act on the algebra. Of course, this algebra can be also represented on a Hilbert space, and that Hilbert space then also admits a group action. So the cross product is now a.
So Erik, how is it you say if you have a representation, then the group is also represented? That's an assumption, right? Maybe not. Maybe there is a central extension or whatever.
So I'm gonna write down the algebra only using the action of the group on the algebra elements.
Mm-hmm.
So I'm not gonna talk about the representation I mean, there is of course a representation, but I think I'm agnostic about the fact whether that is a projective representation or not.
So just now there is a group action by.
There's the group action on the algebra.
Mhm.
And you can think about it as conjugation with some element that acts on the Hilbert space, but which then generates the group. But as I said, I'm agnostic about how that is represented on the Hilbert space itself.
In a sense, it's already a representation. It's just representation actually from the algebra.
The algebra itself, of course, is already a representation, and I already told you about the fact that I can use something like this GNS construction to even label all the states by elements of the algebra. And then, of course, I can also represent the algebra on those states in the same way. But now I can extend the algebra by adding the elements of the group to the algebra in a way where, of course, it also acts on the algebra itself. That's kind of what the semi-direct kind of product would mean. But here's called the cross product and denoted like that. If you then ask what is the space on which this is represented, then what you can think about intuitively is that I take the Hilbert space on which A acts, but I make now it into a set of states that are labeled by the group elements. I can namely act with the group elements on the states. So I'm thinking about, so if A is represented on a Hilbert space H, I can take, well, let me call it H valued functions on G. So I think about it that I have a state psi that is kind of in the Hilbert space, but now I also let it depend on B.
Are there notion of Casimirs or something like that, or things that commute with everything?
Now, actually, one of the things I need to assume here, if I want to, what I want to do is namely construct a new von Neumann algebra that's again a factor. And in that case, I need a free action, first of all. Maybe I'm not answering your question, but something like the center, the things that commute with G.
Not the cousin. Sorry.
Well, yeah. Actually, one of the important things is that the elements that commute with G themselves should also be a factor. So in the sense that they don't, but actually the examples I will be looking at, actually this group will act even transitively in the sense that there's no real fixed element under the group action. So it's only the identity. But you will see the definition that I want to impose here or give that defines this. So what I want to do now is indeed tell you if I act with an element A in this on this, it will be. So I'm now looking at a new state in the Hilbert space, but I'm still thinking about it as a function of G. And the definition is basically that I know how G can act on the algebra, and just denote this by G on A. So here I put the brackets like this. So I have a new element as a function of G, and that new element is taking the old element and acting with G inverse A on this. This is what, well, the mathematicians like to put an inverse here. And I'll explain later why it is useful.
So do you apply G inverse to A?
So entire thing.
To A. So so there's an action of G on the algebra. So I can take A to say G of A times A, but here I wrote the inverse element.
But it's extensor functions, and then it's inverse.
Something like that,
Not a
yeah.
group action. If you put G, then it will not be group action.
the right action then wasn't.
Right, yeah.
So there's a right action indeed, which I'm gonna actually use to give a different definition of the cross product.
Either inverse, a left action, or right action, and then not inverse.
That's right, yeah. Well, that's actually, this will come from a right action in such a way indeed that you have to put it on the other side.
Related to the, you mentioned center of G, and you twist this cross product by a triple cycle that is in centers. When you do define group structures on a product.
I'm sure that there are extensions of this, but I didn't look at this myself, so it's not something that
I was asking if the representation is projective or.
I think the group action on the set of states, maybe you're asking whether there's something here happening with a projected, yeah, and that's probably possible. I don't, not something, this is just the naive definition that you first start from, and maybe extensions like that are possible. So the other thing that, let me think indeed, what I actually can give you different construction actually of the same algebra that already goes a little bit towards what I was saying before, namely that there's some gauging actually happening. So what I'm going to do is actually think about a larger algebra, but then mod out by a group action. So the larger algebra that I'm going to be thinking about, and let me actually put it this. There must be one hiding here. So. Maybe I could have started with an algebra associated to the group, namely the set of bounded operators on the square integral functions on the group. So that is also an algebra. Actually, it's a type 1 factor. But then I can take the normal product. So elements of this
This is type 3 times type 1. Right.
well, actually, this what I defined here can be done for any time. But I will do it later for type 3. But I want to say something about this, namely there's so these are operators that act on states, but the states are functions on, so this algebra acts on state psi, and this is where the bounded operators will act on, because these are as a square integral function on the group. But now I can have another action on this, which I call detail. That's the same group, but it's not the group that I'm going to take the cross product with. Namely, I can take this because there is a representation of the group on let me call it U psi on G. And then I indeed take the right action. So let me act with H on this. So there's some group element H that acts on this, and it maps it onto
GH.
sorry, UH then and GH. That's it. So this group of action I call detailed because it's some group that acts on this algebra. And now the theorem is that if I mod this out by d tilde, by this action, that I get back this crosswalk.
Excuse me, I don't understand. This G tilde is a different group, but you are operating G and H. So like if they were elements.
I know, I understand it's a different group action.
It's the same group.
It's the same group, but it has a different action, because here I thought about, because let's say this way, okay, I should have written down something here. There's also an action of H on psi of G, namely that is equal to psi. Now I do it indeed with an inverse.
Well, it's a usual thing, right? You have some vibration, there is fibers are these psi's and bases is a group, and you act on this on a base you with the right action and you rotate in a fiber.
That's
In
right.
this case, just a product. It's the same construction, right? These two are same construction.
Now here I take the semi-product, direct product, but here I define what it looks like. Here I link this and I have this action on it.
Oh, it's the same after you divide.
That's right.
Okay.
So because what you're basically doing here is that, well, intuitively it's kind of clear, because in this space, G acts here and the algebra acts there. There's still a group action on this algebra, but it's not the same group action as this one. But by modding it out, I'm making the two the same. So I'm basically saying there's a group action on these functions. But now by gauging it, the same group action should also act on the algebra itself.
So when you say you divide, does it mean you take the
Invariance.
invariant?
In the variant. So I'm gonna take this, I'm gonna impose that this is the same state as this one.
Oh, you mean in the representation, but in the algebra,
The algebra doesn't act anymore, of course.
yeah, but you take invariant elements in the algebra as well, right? Or,
No.
Or invariants? Something.
That's right. So I'm sorry, what I'm saying basically, sorry, maybe I should have said it. In the algebra, no. I mean, what I'm saying is that this is what I impose on the states. In the algebra, what it actually means that you indeed have to what I would call gravitationally dress the operators, because you basically have to include in these operators
way I understand is that the right hand side is some kind of gauging of the invariant description. You are gauging the group. Whatever you do, the left hand side is its gauged fixed version. When you look on gauged fixed version, it looks like it's semi-direct product, and there is no action of grouping.
or maybe, yeah.
So that is a gauge invariant description, and this is gauged fixed description. That's the way I feel it.
That's right. So that one, that's why you see the large space and then you gauge it. But if you ask what are the elements of the group, then you have to take basically products of things that act here and here, and then mod out.
You just impose Gauss's law. That's what it is. You impose the Gauss's law, the generator of that group, some operator, and act on psi times f, and say it's zero.
Yes,
That means that you are going to what's called physical space, right? Okay,
that's right.
and then in that space, it's not a product anymore. It is very direct.
Well, there is a way of writing it where you say I transform the group. I think there's actually conjugation here, and then I take Q from. You look actually, the elements of the group have to be gauged like this. So there's some way that you act on the algebra and also take linear combinations of those group actions.
Actually, I agree with Stefan's comment before that the representation, so there will be some projective. There will be some co-cycle here usually.
Anyway, this is just to introduce the cross product. I'm gonna actually do it in an example with this abelian, and then there's not much space for these kind of things. Like co-cycles.
Can I ask, is that not considered a product or a tensor product?
This was a normal product. Sorry, this is the tensor product of the algebras, you mean? Well, I think it's just a cross. I mean, this is called a cross product.
I understand.
Yeah, so I thought the notation here was simply,
It should better be tensor, otherwise you cannot add elements.
oh, yeah, okay, so maybe
The tensor product, it's like elements are one there, one there, so A comma B.
yeah, but here also, I think you're doing something similar in the sense that you have both, possible. And here, as I said, that actually, if you ask what are the elements in the cross product, they're basically also sums of elements in A and in the action on the grid. So this is just a mathematical construction, which I think here I've given you the definition. That was just another interpretation of the same well, the same cross product. Yes, go ahead.
Is this G in physical sense will be a gauge group always? Like related to the space-time coordinates?
So when I'm going to the example where we are in gravity, actually this will be associated to indeed the Hamiltonian associated gravity. So there's a gauge invariance, gauge constraint associated. This will be the Hamilton constraint.
So this will be one of the constraints of gravity.
That's right. And this is why it actually is like a gravitational dressing that is happening. And that gravitational dressing, so I'm going to define now a group that's going to act on type 3. And then by gauging it in this particular way, we're going to get actually into type 2. That is basically the statement. And there's a very natural group acting on
Wait,
it.
but I mean, how can you, so that G tilde then action should be infinite dimensional?
It actually, we're going to look at a real line, a group that is actually just translation, time translation.
That's finite dimension.
Now the group action, so the action actually, sorry, okay, we're not doing diffeomorphism, we're only doing the time translations. So in gravity, also there we have a Hamilton constraint. I mean, there are many constraints, but one of them is just the Hamilton constraint that basically tells you that the whole theory.
One which defines energy.
That's right. So we're gonna define the energy, but we're gonna see that that energy has a gravitational definition, and therefore it has to be sort of introduced in the gauge invariant way. And that actually means that the time variable that's associated to it actually should be a physical time variable. Otherwise, you cannot even define it.
But you need it somewhere, you need a space of metrics or something. You know, in gravity, it's on the space of metrics in a given time slice.
So we're gonna add something that's associated to gravity, or the metric, namely the definition of energy at infinity. So if I think about the fact that I have gravity, I can actually measure the energy at the boundary because of the gauge invariance. So there is actually a way that the energy becomes an observable that we need to add to the theory. Anyway, that's what I'm going to be explaining more as I go along. The point is that we're going to define a particular energy associated to this splitting of the space, which is associated to the energy on this side and there's also an energy on that side. And the problem is with type 3 algebras actually that you cannot define these energies independently, but for type when you add gravity, you can actually. This is going to make it.
I think so. It will end up epsilon, T mu nu equals whatever R mu is. It will be integral.
It will be integral. The integral will be added. That's correct.
Only integral. Okay.
There's one fact I wanted to add still before which is actually useful for the next. Is that when this group is abelian, so let's now consider an abelian group. Then there's also a dual group action. That actually acts on this, the space that I have here. So here I had a space of states that depended on G, and the dual group actually is associated to the space of characters. So you have character on the group G. So let chi of G be the character. So the character basically maps the group onto a number, element to a number. So I can also act now with chi on psi of G. And this will be chi of psi of G.
Well, I was asking you about the continuous assumption. The character is specified by.
That's right. So here you label basically indeed the Casimir. So they will
There are.
but this is for Really, and of course the Casimir is just there's a number of them.
So, but this is specific to a billion groups.
That's right. So this is what I'm saying. This is for the Beating case. And so this dual group, well, it's sometimes denoted by gamma. So and then there's another theorem that I cannot go into detail how it's proven, is I can also take the cross product with this dual group action. So then the theorem is that when I take, so I actually take this semi of this cross product, and now I again take the cross product with this dual group gamma. And the theorem is that this space is actually the same as the space I had here before dividing out. And that actually is quite useful also in connecting these type 3 and type 2 algebras.
How do I see in there square integrable functions on G? It's like because of character.
So the way I kind of think about this is that you actually undo the gauge thing that you did here. You basically add again the functions that tell you how the things are transforming.
Any theory can be made gauge invariant.
Well, we know this in orbifolds as well, that if you have an orbifold which you mod out, there's always another action that when you mod that out, you go back to the original theory. But here actually you add these functions to it.
Yeah.
Yes.
I'm a little bit curious. It looks like an action of some double of a fourth algebra. Of course, now your fourth algebra is some kind of easy, but are there examples of other whatever fourth algebras that you can use in that construction? Something like UQ SL2, right? Well, we famously there are other examples here. You have a group and a dual group, and it sounds like it's a double.
That's an interesting question. I mean, I have a colleague who is indeed thinking about sort of extending all these things in von Neumann algebras to quantum groups and so on. And I don't think that theory has been fully developed, but at least it seems possible. It's certainly an interesting direction to think about. Also because of the way that quantum groups now are appearing, say, in these double-scaled SYK models and so on. People are thinking about these kind of extension.
I think in old days there was a discussion of one algebra. Some of these students, this Polish guy, they were just talking about.
Yeah, but there is this business of whatever compact quantum groups of Voronovich and
That's the Python from Polish. No, I think he was the mining student.
well, that I don't know.
I think so. But anyway, there was this discussion 25, 30 years ago.
Continues. There are works on quantum groups.
So now what I want to do is sort of switch topics a little bit, but I will get back, of course, to the cross product. I want to go indeed now to the construction of type, discussion of type 3 algebras, and in particular what's called the Tomita-Takazaki theory. I think I briefly mentioned it in the first lecture. So here I'm thinking about an algebra which is now a type 3 algebra. So we're in type 3. And then we also are going to introduce a state. That be denoted by omega, which has two properties which are called cyclic and separating. cyclic means that basically there's a completion of, well, taking all the elements of A and acting on omega, that if you complete it by adding limits, that this will be actually equal to the Hilbert space, the entire Hilbert space. So you can generate basically the entire Hilbert space by acting with operate algebras of elements of this algebra. Mind you,
We just need one state and we start acting on arbitrary element and create entire.
that's right. And actually note that I'm acting with algebra elements only on one side of the space. So I'm not actually using the other side. So this actually is a statement that we have a highly entangled state, because otherwise it would not be possible. If you have a state that factorizes in something that lives here and there, then clearly by acting with operators here, I will not generate everything on the other side.
Too much, because for example, in integrable case, if you have a commuting Hamiltonian, some space and so on, if you take generic state and act only by commuting Hamiltonians, you can create entire thing, as long as that state is not eigenstate from the commuting Hamiltonians.
And of course, we assume something about this. This is a polynomial algebra, and that means that it must be equal to the comment, whatever the
Commentant
of its own commentant. So there's some way that you make the algebra as large as possible by adding everything. So you ask what is commuting with it, and then you take anything that commutes with that, and that is what your algebra is. And then it turns out that when you act on that state, you can actually generate the entire Hilbert space. This is true in type 3 algebras, and actually it is a very strong statement about the amount of entanglement that we have in these theories. And actually it's also
A prime is a commutant, right? I forgot the.
A prime is a commutant.
So then by doing this, you also describe A prime Hilbert space.
That's correct. So I act only with A, but any state that can be created with A prime is also in this same Hilbert space. And of course, we know this in quantum field theory. There we also, when we write down the state, say for instance for Rindler space, we know that there's a relationship between putting annihilation operators on the right and integration operators on the left. That's sort of what Bogoliubov transformation is doing for you. And then you know you can generate the entire state. But this is something that was known already before Hawking and Unruh. It basically says something about the amount of entanglement in this
So
theory.
now this is restated in new word entangled. All those days they will not say entangled, they will just say that's the Bogoliubov. So all states in the new one are inside the first. That's what they would say.
That's correct.
And the operator that does it need to be called identificator. Identify.
Yeah, but one of the important facts here is that when I act with a unitary operator on the right-hand side, there's not I cannot get the state that I can obtain with unitary operators on the other side. Let's say this way, it's a different state. So you cannot have a identity between a unitary operator on the right. So if I want to, maybe I said this, suppose I act with a unitary operator here on the left, I can create the same state by acting on the right, but it will not be with acting with a unitary operator. That's not possible. So I cannot find a unitary operator here that creates the same state.
That identification is not done by unitary operator. So we have, let's say, this is a state. Think about workspace, right? Some kind of workspace. Yeah. Inside there is a vacuum or whatever, the ground state of the other. So the operator that map this one to that one usually is supposed to be a unitary operator, and then inside another workspace you can write everything by acting on the first one with unitary operator, this identification. Now you are saying that if that guy and the first guy, if I have a unitary operator in one and another, they not be unitary equivalent to each other.
So yes, so it's not possible to create all states by just unitary operators.
Is there an anti-unitary equivalence?
No, but there is I'm gonna define now an anti-unitary operator for you, but it's not one that I. Well, okay, I'm gonna define a map indeed from the algebra to its commutant, which is by an anti-unitary operator. Anyway, let me make those statements, but
Does it mean that H is just a reducible representation of A?
that's correct, but the surprising thing is, and this is actually encoded in what's called the Riesz-Leader theorem, that if you have a type 3 algebra quantum field theory, that you can take a little part of your space, act with all the operators in that little part of space, and you can generate the entire field.
But you have a slide that you can just.
Oh, sorry, excuse me, Sergey. This last statement, I just wanted to, not this last statement same as Heisenberg, we know that we have phi at point x and we can write it as from phi by point 0 by acting of exponential of minus IH.
Basically that's basically it, and actually you make use of the analyticity properties of the vacuum, that the fact that if you have namely a function that's 0 in a finite part of space, it's 0 everywhere. And so
Yeah, but I mean, if it's a irreducible representation, then the statement should be correct for any vector from H.
Yes.
Yeah.
that is
You can
true.
use any vector, not some special vector omega, and then you.
Oh, no, omega, I think he chose to generate the space. So he says, I don't think.
No, but you're right that a lot of things will be independent of this vector. So there will be other vectors that have the same property.
Yeah, almost everything will be independent.
That's right. So that's correct.
Yeah, well, but in usual field theory, vacuum still has some special properties.
Can you not say it was a
There is
vacuum?
also the Hamiltonian
Wait a
and.
minute. Can you not say omega was vacuum? He just says, I need one state, only one state. And acting, actually, in the chiral rings that you know in superspace cells, you just need to check what you have. You just need one state, and then you have by operators.
Yeah, but
I,
that's the finite dimension.
That's finite dimension analog.
Yeah.
What I'm saying is, you did not say that state was vacuum yet. You did not introduce yet.
I'm just basically saying what its properties are. The other one I mentioned was separating, which is also a very important one, namely that if A is 0, acting on this is 0, then A must be equal to 0. So if A annihilates the
generates,
then this must be so there's no operator basically that annihilates if you only take an element of the algebra.
yeah, so you need to start with such omega. It's not a statement about A, it's a statement.
But there are many of these omegas, and what I'm going to be introducing now is a group associated to omega, but we will indeed find out that the group action essentially does not depend on omega. It's going to be universal. So the question about the antilinear one is actually an interesting one, because that's actually what I'm going to introduce, is namely the Tomita operator, which is unitary, linear. Linear, let's say, Tomita operator. Namely, there in the algebra we had an operation which is called star, namely that you take the conjugates. And this statement that I can generate the entire Hilbert space is also true. Yeah, it's also true for the A star. And so there must be a map which maps state A on omega on A star.
Does it have anything to do with time reversal?
Yeah, so there is some way in which, but there's also a way in which we actually exchange A and A prime. So this thing does two things. It actually is something like a time reversal, but it also flips the two sides. Because this operator has a number of properties. There's also namely a conjugate operator. An important thing you see from here, by the way, is that the square equal to 1. But there's also a conjugate operator. And there's a number of properties that we can actually derive, and due to time, I'm going to be brief about this. I could have done the same thing with the commentant operator, the algebra, which is the commentant. So I could have also defined an operator that is as omega prime, and it turns out that that is exactly what is the conjugate of this operator.
Just clarification, I'm a bit confused why you no longer denote by star. So this cross is the same as a star or not at all?
So this is an operation on the algebra,
But
as is not an element of the algebra.
yeah, right. But on your Hilbert space, this would be a Hermitian conjugation. This cross, is it right?
Yeah. So what indeed it has the definition that the usual definition. Although the thing that I mentioned that is antilinear is kind of tricky because emission conjugation actually has an additional star in it. So there is the definition that if I have a state psi here, S, and here a state psi prime, that this is equal to psi prime as dagger psi without the conjugate star.
So why as long as there is independent of A,
Sorry?
why is as omega independent of A?
Also, this is a map from this entire, all the set of states is going to be mapped onto the set of states.
Of course, this depends on me.
No,
So then why it's so this kind
Well, no, it depends on capital A. It depends
also
on-
it's like it depends on
Capital A is element in capital A.
that's right, yeah. So this is an element in A, but so star is basically a map from A to A, which squares to 1. And this is the map that acts on the states that I create right then. So if so A, it also does this, of course. And this is why it squares to 1.
Actually, what is not clear is why S prime, which is the object in A prime.
No, actually, S is neither an object in A nor in A prime.
S is defined in terms of omega.
Yes,
Omega is element in A.
yes.
There is another element in A prime, let's call it omega prime.
Omega is a state.
Omega is a state, so it's common for A and A prime.
That's right. So the A and A prime act both on
Same state.
on the same state.
Okay, then it's clear S prime can depend on omega.
So as we just discussed, I mean, if I act with A on omega, I'm also generating all the states that I would have obtained by acting with A prime on omega.
Yeah.
And actually by acting with sums and everything.
I just missed the point that omega is shared, of course. It's
Anyway, I think it should be maybe.
Yeah, maybe.
10 minutes.
Yeah, okay.
I mean,